So, would you like me to start?
Absolutely.
Yes, thank you so much. So let's get started. Dear students, today we will talk about Young's experiment. Young's experiment is very important experiment in physics, and it showed that light is a wave, and it has the wave properties. So we know that Huygens and Newton had different ideas about that. So Huygens believed that the light is a wave. However, Newton was thinking that the interference and diffraction can be interpreted using different idea than Huygens did. But then in 1800, there is a scientist, a British scientist, his name is Young. He came with very nice experiment, which is the double slit experiment or Young experiment. And he performed this experiment and got very nice interference pattern. So now what we are going to do, we are going to explain this experiment. So let's go ahead and explain that. So before I talk about this experiment, it's a good idea to introduce two important topics. The first topic is the single slit or the single opening experiment. And the second thing is to talk about Huygens principle. It's very important. So without those two, you are not going, or you will have hard time to understand the double slit experiment. So let's start now with the single slit. What we can see here, so simply we can see here a single slit, as you can see right here, and also the single slit here has a width, as you can see. Right here we have a screen, and we will use the screen to receive the light from the slit. Actually, if we have incoming light, and this light can be laser light because it has one wavelength, or you can use the light from the sun because the sun is far away enough to receive kind of plane waves. So if we allow this incoming light to go through the slit, the result will be bright region that you can see right here. So this is bright region. But the shape, the width of this bright region depends on very important factor here, which is the width of the slit. If I control the width of the slit, I will notice something very important. So what is that? The thing that I can notice is that if the width of the slit, for example, is larger than the wavelength of the incoming light, so what will happen? You will have this kind of intensity. And by the way, here we have a distance which represents the width of the screen, and here we have the light intensity. And I try to show you that in 2 dimensions, so you can link the intensity, to the width of the screen. So if the width of the slit is larger than the wavelength of the incoming light, so what will happen? You will have this kind of bright spot, like this. If I try to decrease the width of the slit, so what will happen? You will notice kind of change, not in the intensity, but kind of change in the width of the bright spot. So it will be a little bit wider. If you have the width equal to the wavelength of the incoming light, so what will happen? You can see that the bright spot will be a little bit flattened. So it will be a little bit flattened. If I continue to decrease the slit, what will happen? We will have this pattern that you can see right here. So we will have at the middle, the highest intensity, bright spot, and then we will have 2 dark fringes, And then we will have after that two bright fringes. So you will have kind of pattern like this. So you will have bright fringes and dark fringes, and I will show you that using the simulation. But the middle one is the brightest one. And if you go to the right and go to the left, you will notice that the intensity will go down. So this is pretty much everything about the single slit, so you understand what will happen here. And there is another important thing. If we are talking about single slit here, that means we are talking about diffraction of light. What do you mean by diffraction of light? So the diffraction of light means that after the light goes through the slit, what will happen? The light will spread, and you will notice, so the light will spread, and you will notice the light will not have the same straight lines that we have before the slit. So you will have kind of spherical wave fronts, or like spherical waves. So this is what you will have on this side, on the right hand side. However, on the left hand side you will have plane waves that are coming and then incident with the slit. So diffraction, that's good. Now let's move here, and I will prefer to move the camera here so you can see that a little bit clear. So here I have another figure that can help you to understand Huygens principle. So what do we mean by Huygens principle? What I have here, I simply have the one slit. So here is the opening. So we have the one slit, and then what do we have? We have plane waves, of course, with the wavelength lambda. It's a good idea to use laser source, so that can be very nice. And the most important thing that I will need to mention here is that this opening here is very narrow. So that is a condition. We need to have W smaller than lambda, so that can give me this kind of pattern that you can see. So after the plane waves go through the openings, what will happen? You will see that this opening here, or this slot, will be considered as a source of spherical wave. And you can see those spherical waves going and then propagate in all of these directions. And another thing that I would like to mention here, each one of these half circles that you can see, which represent the spherical waves, can be called wave fronts. So this is a wave front, this is a wave front, and this is a wave front, and this is a wave front, and this is a wave front. All of these are wave fronts. And what Huygens told us that each point on the wavefront can be considered as a new source of spherical waves. And this is a very nice, actually, very nice achievement here. Also, if we go back to the plane waves, so each one, or each point on the plane waves can be considered as a source, as a new source of a spherical wave. So this is what Huygens told us, and this is very nice. This can help us to understand a very important thing, which is interference. So now, let's go to the double slit, and before we go there, let's try to have this idea in our mind. So one slit can give us those spherical wave fronts. What if we have two slits? So what will happen? So that will give me two sources, and each one of these sources will give me spherical wave fronts. So there is kind of interference will happen, and I will show you that using the simulation. Of course, this interference will happen between those two spherical wave fronts. So now let's come down here. This is the double slit experiment, or Young's experiment. Here we have the double slit, and here we have the screen. So the screen can be used similar to what we did before with a single slit. It will be used here to receive the light from those two slits, or the interference result. So again, we will have here plane waves coming to the double slit and then hits those double slits and then go out. So when they go out, you will notice you will have two sources of spherical, as I mentioned, two sources of spherical wave fronts. And there's interference will happen here. And when the interference happen, you will see that the screen will have kind of strange pattern. It's not strange, but it is new for us. So you will see that you will have dark, bright, dark, bright, dark, bright, dark. And that can continue. That depends on the wavelength, the distance between the double slit and screen, and some other factors. So, but the most important thing, you will see that you will have dark, bright, dark, bright, dark, bright pattern. So that's great. And what's the reason for that? The reason for that is the interference. So this idea is correct now, and Huygens supported Young's idea, and also Young's idea supported Huygens. So you can see now that Newton was wrong, yeah, after this long time, of course. Yeah, but since we understand what will happen in the double slit experiment, it's a good idea now to go to the geometry. So geometry is another important thing to understand the double slit experiment. So I have the double slit. So this is slit number one, slit number two. There is a distance between them. And here we have bright point. So this point can be bright point, like constructive interference, and also it is possible to be dark point or dark fringe, destructive interference. So that's possible. But let's choose this one and see what will happen now. If we try to have a contribution for slit number one to this point P, and the distance between the slit number one right here and this point is L1. Another contribution from slit number two, and the distance is L2 between slit number two and point P. So we can see that we have L1, we have L2, and of course we should have a little bit difference in phase. But if we have phase difference, so that will give us here like dark spot. If we have, for example, if we don't have, or if we have those two waves as in phase, so what will happen? You will have bright spot. So it can happen here in the two cases. The other thing that we need to keep in mind, we know that there is an angle theta prime between L1 and the horizontal line. There is another angle theta between L2 and the horizontal line. And for this situation, or this experiment, is a good idea to have theta close to theta prime. So that can help you to have like very small difference between L1 and L2. And if we have that, so this is L1 and this is L2, you will notice that this is the difference. And of course the difference is d sine theta. Since this theta, so the difference would be d sine theta. So now d sine theta is equal to delta L, which is the difference between L1 and L2. And now delta L here, what do we mean by delta L? Delta L here can be a key to know the constructive and destructive interference. How can we know that? So if we have constructive interference, so delta L actually is integer number times the wavelength of the incoming light. If we have dark spot or dark fringe, so what does that mean? That means delta L is equal to m plus 1/2. It is integer, it is a number also, times lambda, which is the wavelength of the incoming light. So this is how can we understand this experiment, and this is how can we support Huygens' idea using the double slit idea or Young's experiment. So now we understand what can happen geometrically, and also we understand what can happen here, not experimentally, but with using this figure. Now let's go to the simulation and try to show you what exactly happened if we have interference. And of course, in Young's experiment we have two important properties here, diffraction and interference. The diffraction can create those spherical wave fronts, and the interference can create this nice pattern that you can see here.